Hello everyone. My name is Diandian Wang, and in this very short video, I'll be going over this poster on work in progress with Daniel Jeffers and Lisa Rosenberg. So the idea of the work is to construct a model for 3D gravity with end-of-the-world branes uh, by studying a random ensemble of boundary CFTs. So this is largely inspired by a lot of recent work on 3D gravity and more generally lower dimension models of quantum gravity. So in particular, in reference one, a tensor slash matrix model was constructed from knowledge of 2D conformal bootstrap. So that turns out to be a model for 3D gravity because the Feynman diagrammatics gives rise to 3D gravity partition functions. So this model has two parts. There's a tensor part that essentially corresponds to a Virasoro TQFT, and there's a matrix part that computes contributions for off-shell topology that is finite, whereas Virasoro TQFT would give an infinite divergent answer. So our goal is to extend this to a random ensemble of BCFTs, which are CFTs with boundaries. So what we find is that the tensor part of the model now gives rise to a what we call open-closed Virasoro TQFT. And the matrix part describes off-shell topologies, but now for gravity with end-of-the-world branes. So in this first section of the poster, we review what data we need to define BCFT and what the bootstrap conditions are. Moving on to the next part, we essentially follow the idea of reference one by integrating over all the variables we need to define the BCFT to define this tensor matrix model. And the potential here is obtained by squaring each of the bootstrap constraints and adding them together. So there are two parts of this potential. What we call V0 is essentially the matrix part of the model, and what we call V is the tensor part of the model. So in the next section of the poster, we explain how the tensor part of the model gives rise to a open-closed Virasoro TQFT. So it is open-close in the sense that when we glue two blocks, TQFT blocks together, we do not have to glue along a closed 2D surface. And at the end, we present all the basic building blocks we need to construct this TQFT in a bottom-up approach. So after doing that, we move on to the matrix model. So here, similar to in reference 2, where they square the 0-point torus constraint, we square the 0-point annulus constraint as well. And then we obtain, by squaring with the appropriate inner product, we obtain this expression. So here we get different diagrams that would correspond to predictions for contributions from off-shell topologies. So I think that's all the time I have. Here's a summary and references. I hope this helps you with reading the poster. Thank you very much.